Hypothalamus, artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for decision-making, artificial intelligence, and disaster and emergency management. Part 1. Events due to nature. Framework. The challenge. Develop a DSS for disaster and emergency management. The overall objective is to minimize potential negative economic impact and human life losses. The solution. Design a set of mathematical models to address the problems arising from disaster management based on stochastic programming models. The benefit. A set of measures and mathematical models to prevent and/or reduce the impact of disasters, and it prepares the community to respond in the best way when a disaster strikes. The general approach of HI is to connect predictive and prescriptive analytics models, which implies an integrated holistic vision, multidimensional space-time, of the entire supply chain of disaster response services. Predictive analytics is based, mainly, in artificial intelligence, machine learning, and complex probabilistic methods. Prescriptive analytics in mathematical programming, better known as optimization. Activities to ensure safety. These mission areas may be grouped based on when a defensive action is intended to occur, either before, during, or after an attack. Proactive planning. Mission areas whose defensive actions are taken before an attack occurs. These mission areas are prevention/protection and mitigation. Real-time operational planning. Mission areas whose required actions are taken during or immediately after an attack. These mission areas are detection and response. Recovery planning. Mission areas whose required actions occur after an attack. This mission area is recovery. Natural disaster management. The mitigation and preparation of disasters caused by nature implies. The overall objective is to minimize the potential economic and human loss, and continuity of operation of the economic system. To this end, the historical behavior of nature is studied, trying to know probabilistically what can happen in order to make decisions of where, when, and how to allocate resources to mitigate and/or prepare for the disaster. Actions before mitigation, set of measures to prevent or reduce the impact of disasters. Preparedness, preparing the community to best respond when disaster strikes. Given the uncertainty regarding disasters, the theory indicates that the only way to prepare for disaster is to probabilistically characterize risk, with predictive analytics, and based on that information to make optimal decisions on how to mitigate it, and how to prepare for it, using prescriptive analytics. The process involves making decisions in advance, regardless of any future scenarios, and simulating decisions for each of those scenarios. The decision should consider the expected value of the benefit, or the cost, and the control of extreme risks, which should not be assumed. The process of stochastic optimization involves 3 stages, 2 of predictive analytics. Stochastic process model converts historical data into a dynamic probabilistic model, and synthetic scenario generation turns the dynamic model into a synthetic scenario tree. When there is enough data, these 2 processes can be algorithmic, otherwise it is necessary to resort to a committee of experts. And 1 stage of prescriptive analytics. Stochastic optimization, it converts the scenario tree to here and now decisions, and with the simulated future decisions generates probabilistic distribution functions for the future. The model should include extreme risk control constraints. It is suggested to use the conditional value at risk as a risk indicator. In this case, the decisions to be implemented are associated with the optimal resource allocation policy for mitigation and preparation. Actions after reaction, the use of resources and emergency procedures to preserve the life, property, and environment of the community, since the disaster is occurring. Recovery, set of long-term actions to stabilize the community and return to normalcy. The reaction and recovery after the disaster occurs implies actions during the disaster, and reconstruction actions. Earthquake Management in Seattle. Pacific Rim Visualization and Analytics Center, PARVAC. It is made up of the following computer components. GOSR, Geospatial optimization of strategic information and resources. Platform of mathematical models and numerical algorithms for decision support in emergency management. JIC3, Just-in-Time Mobile Command and Control Environment. Command post for the deployment of personnel in emergency response, to optimize the flow of information about the emergency and response during an emergent event. RIMSIM, First Response Simulator for Common Pacific Rim Threats. Software based on a modular system, to simulate first response communications, common artifacts, and response actions in order to evaluate and improve the level of distributed knowledge, and VisSearch, Visual Search Aid System, by means of image or pattern detection strategies and technological mediation. Decision support systems for disaster preparedness and response are challenging because uncertainty of events and difficulty obtaining real-time data. GOSR development optimization models for the location and allocation of medical supplies to be used in emergencies for the Seattle region. The distribution of supplies requires at least the decisions before the event, location of warehouses, and inventory levels of medical supplies after the disaster. Optimized allocation of medical supplies to hospitals to reduce delivery time. In the preparation stage, RIMSIM and GOSR integrate personnel training into a disaster command center. RIMSIM is used for simulation of the training environment, on the other hand GOSR is used for optimal decision making. In the response stage, GOSR is used for real-time transportation decision making, while supply-demand information of the disaster is collected. The models to use previous to disaster are Stochastic Optimization Model, selective warehouses, and determine inventory levels by balancing disaster risk with on-time delivery of supplies. Transport Model, transforms transfer orders into optimal vehicle assignment and routing. In the response phase, the fundamental model is Real-Time Optimization Model. It results in the allocation and routing of vehicles with up-to-date information on transport conditions and current demand and supply information. In this academic example, 2 Seattle earthquake scenarios were considered for the analysis: Seattle fault, M6,7 with probability 0.6, and Cascadia fault, M9,0, with probability 0.4. Additionally, it was considered 3 warehouses, 10 hospitals with demands of health services depending on the fault, 62 routes that connect warehouses with the hospitals, and 1 type of medical supply. The table presents the results obtained for the preparation stage, including inventory levels in each warehouse, expected quantities transported between warehouses and hospitals, and routes used. Inventory levels are decisions variables here and now, and they are independent of failure. Transport flows depend on each scenario, they are simulated variables. Case: Earthquake management in Istanbul. Case: Rebuilding New Orleans. Case: Seismic risk management in Italian Tuscany. The document: Earthquake risk management via stochastic optimization, a case study for an Italian region. It describes how a stochastic spatial dynamic optimization model, which considers the complexities and interdependencies of catastrophic hazards, has been customized to explicitly incorporate the geological features of a region, the parameters of seismic hazards, and the vulnerability of the built environment. The model can analyze the interaction between investment and mitigation measures, and risk-sharing measures. Special attention is paid to the evaluation of a multi-pillar earthquake loss propagation program, involving the central government, and mandatory insurance. It is shown that the model can analyze multiple policy options, to develop insurance policy in an equitable and fair manner, and their effects on insurance premium and reserve funds. To analyze system stability, EASA uses a strong connection between non-differentiable stochastic optimization and risk measures such as value at risk and probability of insolvency. These data have been incorporated into a Monte Carlo generator of seismic events, which simulates the occurrence of earthquakes affecting the region, calculates the attenuation according to the geological characteristics, and finally determines the acceleration in the ground in each municipality. EASA's stochastic spatial dynamic optimization model has been customized to explicitly incorporate the vulnerability of the built environment, with data on the number and types of buildings in each municipality. In the first phase, the study has been limited to the study of different policy options for an insurance program. The next phase investigates the interaction between investments in physical mitigation, retroadaptation, and risk-sharing measures. The document: Detecting Critical Nodes in Forest Landscape Networks to Reduce Wildfire Spread. It is the source of the information presented in this section. Mathematical modeling to reduce wildfire spread. Wildfires are an important ecological process in forested regions around the world, which can cause significant economic damage and often create widespread health impacts and environmental pollution. A network optimization approach to planning combustible material treatments in wildfires that minimize the risk of fire spread, in wooded landscapes below an upper limit for the total area treated. Simulation models are used to estimate the probability of fire spread between pairs of forest sites, and a critical node detection (CND) model is formulated that uses these estimated probabilities to find a pattern of combustible material reduction treatments that minimize the likely spread of fires through. Mathematical modeling controls the size and spatial contiguity of combustible material treatments. The authors demonstrate the approach with a case study in Kootenay National Park, British Columbia, Canada, where they investigated prescribed burning options to reduce the risk of wildfire spread. The results provide new insights into cost-effective planning to mitigate wildfire risk. The approach is applicable to other ecosystems with frequent wildfires, and to the design and redesign of industrial and/or environmental forests. Detection of critical nodes in a network of flammable forest sites. A forest zone can be thought of as a connected network of flammable areas, nodes, where connecting arcs, edges, represent possible vectors for the spread of fire between adjacent areas. To minimize the chance of fires spreading widely throughout the area, the administrator assigns a set of treatments, prescribed burns, between the nodes. Treating a node helps reduce the intensity of the fire for more effective suppression. For simplicity, it is assumed that treating a node is equivalent to removing the node and all arcs connected to that node from the forest network. It should be noted that treatments are not always completely effective. The administrator's problem is to determine the best way to divide the network to minimize the likelihood of fire spreading. A popular strategy to solve this problem is to reduce connectivity between nodes with flammable fuels in the forest area. This strategy can be implemented by solving a critical node detection (CND) problem, which finds critical nodes in a network whose removal degrades network connectivity to the maximum according to a chosen metric. The concept of critical nodes characterizes the vulnerability of a network after a portion of the nodes are removed, which, depending on the type of network, could be the result of natural disasters or technical failures. The CND problem has been applied in many disciplines, including security applications, transportation, social network analysis, and epidemiology. Let G equals n, E, be a graph with a set of n nodes, or vertices, and a set of edges E, n times n, Fig 1a. Two nodes I and j are connected if graph G contains a path between them. We define a connected component of graph G as a subgraph in which each node has a path to all the other nodes in the component, but not to any node outside that component. A G graph is fully connected, and represents a single connected component, if all of its nodes are connected in pairs. If there is a pair of nodes that are not connected, then graph G contains at least two connected components, figure B. We define a binary variable 11, 0, 1, I equals 1, n, 2n, where 11 equals 1 if node I is not removed from the graph G and 11 equals 0 otherwise. A binary variable, ui, j, 0, 1, is defined for each pair of nodes I, j, ui, j equals 1 if nodes I and j are not removed, i.e., 11 equals xj equals 1, and there is a path connecting I and j, i.e., when nodes I and j are in the same connected component, figure 1c. The images shows the following graphs. Graph A, a horizontal network of areas, graph, connected as a single component connected prior to interdiction. Graph B, an intercepted graph with two components connected. Large dots denote the deleted nodes, and graph C, pairwise connections between nodes and the connected components after interdiction, dark blue lines. In the context of fire prevention, the existence of a path between nodes I and J means that a fire could spread between I and J. The area of a node I is C. The subset of nodes that can be removed from a G graph is limited by an upper limit treatment area limit B, which also defines the total cost of deleting nodes. The graph obtained after the removal of critical R nodes is a subgraph sub G composed of the set of remaining nodes, NR. A typical and, in the case of fires, very relevant to the CND problem is to minimize the total number of pairs of nodes connected in the remaining components, subgraphs, after the removal of the critical G nodes. The formulation of the CND problem based on Varamiev et al. Is shown on the image. There are several variations of this model, so that it is applicable to real problems. The objective function minimizes the expected number of node pairs, between which fire propagation is possible after the removal nodes in the G network. When nodes have the same area, upper bound B limits the total number of nodes removed. The subset omega I includes those nodes J that are potential targets of fires, starting at node I, with probabilities of fire propagation Pij greater than 0. Constraints only consider pairs of nodes with non-zero probabilities of fire propagation. For each pair of I and J nodes, the target function tracks the Uij and Uji route connections, and the probabilities of Pij and Pji fire propagation in both directions, helping to account for differences in the directional spread of fires. For example, the probability values Pij greater than Pji could characterize the spread of fires between nodes I and J, with prevailing winds blowing from I to J. The image shows Figure A, node pairs Ij with the origin and node I that are evaluated in the basic CND problem. Figure B, potential spread area of fires ignited in location I. Nodes with the positive probabilities of a fire spread from the ignition node I, are shaded. Figure C, probabilities of a fire spread from node I with the ignition points to nodes J, Pij. Fire spread examples in Fig 2A and 2B are based on 100 iterations. Figure D, a fire shed around the node of interest J, and Figure E, using auxiliary node 0 to inject the flow into the landscape network. Dashed arrows show the arcs connecting adjacent nodes N. Arrows in bold red show the flow from node 0 through the connected nodes scheduled for removal, outlined in red. Case study: Kootenay National Park, British Columbia, Canada. The CND model was applied in Kootenay National Park in British Columbia, Canada. The maps show the location of Kootenay National Park and its main features. The park is part of a UNESCO World Heritage Site in the Canadian Rockies, and covers a subalpine and alpine region, with elevations between 1,200 and 3,400 meters above sea level. Forests at lower elevations in the area are dominated by Engelmann's fir, subalpine spruce, white spruce, and palo pine, and are replaced by alpine tundra at higher elevations. Lightning ignitions are a common cause of large fires. The Canadian Burn P3 model was applied to simulate ignitions, and fire spread in the Vermilion Valley area, approximately 834 square kilometers, under the current management regime. The Burn P3 model generates stochastic fire ignitions and spread scenarios, which uses the Canadian Fire Behavior Prediction System, FBP, canopy fire scheme, modeling surface fires as well as the transition to canopy fires, and the rate of canopy fire spread. For each iteration, Burn P3 generates the ignition locations and perimeters of the individual fires. The Reimer et al. Fire regime is used, which assumes that fire management teams attack all fires detected in the area but, on average, 13% of ignited fires would escape the initial attack. Fire suppression has the greatest impact on fires that are small at the time of discovery and is substantially less effective when fires are already large. For example, Alberta reported 83% success in containing fires smaller than 3 hectares, and British Columbia reported 92% success in containing fires smaller than 4 hectares. A 5-kilometer buffer was added to allow fires to spread in and out of the study area. We calibrated the model to align generally with the historical fire size distribution in the Vermilion Valley area from the Canadian National Fire Database. The terrain network, G, includes 834 hexagonal nodes of 1 km2, interconnected in a triangular pattern. The size of the nodes must balance the numerical complexity of the problem, with its practical usefulness for real planning. It is an appropriate size to capture the patterns of natural fire barriers, such as individual mountain ridges, or rock outcrops, which have proven to be effective barriers to fire spread in the park, at a scale of 250 meters, and greater. Based on this fixed node size, the limit of treatment area, B, defined the number of nodes that would be removed from the network. The optimization model can be applied to evaluate two different scenarios. Probabilistic uses the unchanged probability values Pij to scale the Uij decision variables in the target function. In this scenario, Ij node pairs exhibiting the highest fire propagation frequencies have the greatest impact on the target value. These frequencies depend on the size distribution of the fires that ignite at node I and propagate to J, since fires started at I must be at least as large as the distance between I and J. In a forest landscape, the distribution of fire size follows a general function of the power law. Consequently, this scenario tends to be intersected by geographically distinct hot spots with small but frequent fires throughout the landscape, and binary. The values of Pij and the target function are replaced with binary fire propagation indicators, Pij bin, which are equal to 1 for Pij greater than 0 and 0 for Pij equals 0. Therefore, the scenario assumes equal unary weights for all node pair connections with Pij greater than 0. For each node I, the sum of the values of the bin Pij defines the possible extent of propagation of fires started in I, a fire basin area that the scenario minimizes. For a typical gridded network of forest sites, the number of connections between pairs of nodes grows in quadratic proportion to the linear size of a connected component, and thus the distance between a pair of nodes I and J grows. Consequently, the binary fire basin scenario minimizes the number of long paths between pairs of nodes and thus minimizes the spread of large fires. The probabilistic and binary flourished scenarios can be viewed as alternative strategies for minimizing potential fire spread. Graphs show the fire size distribution generated by burn P3 versus the historical fire size distribution from the National Forest Fire Database, NFDB. Graph shows fire spread probability, Pij, between a pair of nodes versus distance between node centers. Red line is a power law approximation for Pij as function of the distance. Y-axis is shown in log square scale. The table presents the scenarios analyzed with the optimization model. Maps of optimal node removal solutions. Key fire regime metrics. Graph A, burn probabilities. Graph B, fire spread probabilities between node pairs, Pij, spread probabilities along network edges E between adjacent nodes are not shown, and Graph C, fire spread probabilities between adjacent nodes, Wij. The results of node removal solutions, based on land cover configuration, are presented in columns for three values of B, equal to 10, 20, and 30 nodes. Each column has 3 rows of maps for 3 variables for scenario 1. The panels of D through L show solutions, which ignored spatial contiguity constraints for site treatments, for treatment area, node removal. The solutions without fire spread information, D to F, split the central Vermilion Valley almost in half, while the rest of the budget was spent on isolating small valleys connected to the central valley by narrow corridors. As the treatment area limit B increased, a larger share of the budget was spent on isolating these small valleys. Incorporating information about fire spread changed the optimal node removal patterns. In the binary solutions, G to I, the central Vermilion Valley was not cut in half. Instead, the immediate focus at lower budget levels was on isolating the smaller valleys. As the treatment area increased, the model fragmented the area with high risk of ignitions in the southern part of the Vermilion Valley. The probabilistic solutions of the fire basin differed from the binary solutions of the fire basin, J to L. Most of the budget was spent on the partition of the area with an elevated risk of ignitions in the southern region. At the larger treatment area level, a small portion of the budget was allocated to the creation of one, or two, large divisions in the north. Compared to binary fire basin scenarios, no budget was spent on disrupting the narrow corridors connecting smaller valleys. In general, probabilistic scenarios more effectively reduce the local spread of fires between adjacent nodes than binary scenarios. Climate risk management. Case, sowing planning. One of the important risks, in which all companies are involved, is associated production processes in the bioindustrial sector, which are seriously affected by hydroclimatic conditions, whose volatility is increasing because of the global warming that is occurring on our planet. This situation means that the risks associated with the industries, whose financial statements depend largely on the climate, must be assessed and managed. The biggest problem for companies in the sector is that they must intervene in the process of sowing and harvesting bioindustrial products, since the management carried out by the operator derives the risk that a third company may end up assuming. Ignoring this situation can lead to a significant reduction in economic benefit, for a private company or a state-owned enterprise. In addition, the high geospatial correlation of climate must be considered, which increases risks, and the concentration of risks in a region, or in a type of product, must be carefully considered. Public health systems optimization. Mathematical algorithms for epidemic management, based on high-complexity mathematical methodologies, will prevent the most deaths. Public health management implies challenge, to design and implement a DSS to pandemic management. Solution, design and implementation of a DSS aimed at pandemic management integrated by the following high-complexity models. Epidemic simulation model. It simulates the spread of the epidemic as a result of a mix of control policies to deal with the epidemic, mitigation, confinement, and vaccination. Modeling divides the territory into regions, the population into socioeconomic segments, and time in seasons, in order to have a dynamic epidemiological model including multi-infected states, multi-region mobility, and multi-socio-demographic segment. Epidemic management optimization model. It optimizes control policies, the use of health supply chain, HSC, resources, the optimal expansion of HSC vital components, bearing reference to the epidemic control policy optimization model, and the vaccination processes. Epidemic socioeconomics impact model. It determines the socioeconomic impact of pandemic control policies on the economy. Integrated with our S/OPT, it can produce dynamic pandemic control strategies that balance those contradictory objectives that may arise in the epidemic management process, minimize human deaths and maintain the economic's health. And epidemic state estimation model. Hybrid predictive analytics model, based on the distributed Kalman filter, to track the pandemic. Pandemic management optimization process implies research in the following areas: epidemic theory, smart sampling, identification of epidemic model parameters and the epidemic state, and mathematical programming optimization models oriented to control and management of the pandemic process. High health integrates with high RPO, regional planning optimization. This implies that all models of the two systems can be integrated through the database, common data model, or by means of equations that integrate a unique holistic model, this following the principles of structured mathematical modeling. This integration is since the management of public health problem corresponds to regional planning problem, as experienced during the COVID-19 pandemic. Anticipation. It is the core of decision-making under Environment 4.0. It is not a question of reconstructing the damage caused by a disaster, with decisions a posteriori. It is about anticipating and mitigating with actions before the disaster. And the best way to do that is to use the mathematical modeling power under the new technological paradigm. Like Carl Friedrich Gauss, hypothalamus artificial intelligence believes that mathematics is the queen of the sciences. Thank you for your attention.